Calculus. Welcome to section 4.9, where we study related rates, one of the most important applications of derivatives. In related rates, we're going to find the rate of change of one variable when we know some of the others. There are multiple steps to this problem. Make sure you've read through these steps in your notes, and we're going to do an example together. These examples can be kind of long. A police cruiser is chasing a car that has turned the corner as shown in the diagram below. When the cruiser is 0.6 miles north of the intersection and the car is 0.8 miles east, the distance between them is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour, what is the speed of the car? Pictures are very helpful. If a problem doesn't have a picture, I suggest that you draw one. Then look at what you know. We know that x equals 0.8. That's the distance of the car from the corner. We know that y is 0.6. That's the distance of the police cruiser from the corner. S is the hypotenuse, or the distance between the vehicles. I suggest that you find that right away with Pythagorean. 0.8 squared plus 0.6 squared equals s squared. Solving for that, s is 1. Then we can look at rates we know. dy dt is the rate of change in distance from the cruiser to the corner. That's the rate it's changing over time. That's negative 60 miles per hour. And it's negative because he's getting closer to the corner, so it's decreasing. And then we know dstt, the rate of change in distance between the cars. That's given to us as 20 miles per hour. What we're looking for is the rate of change of the other car. So we're looking for dx dt. We need to write an equation and differentiate. Since this is a Pythagorean problem, we're going to start off with the Pythagorean theorem. So x squared plus y squared equals s squared. And we actually evaluated this out at first using numbers, but remember, we're looking for a rate of change, so we have to differentiate before we evaluate or substitute anything else in. So differentiating this, 2x dx dt. We're doing this in relationship to time. So every time you take a derivative, you're going to put the appropriate derivative term next to it. Plus 2y dy dt equals 2s ds dt. So all we did was took the derivative. Now let's take that and let's evaluate it out based on what we know. So again, here's what we just had as our derivative. Okay, so there's our derivative from the previous page. So looking back, if you have to, at that previous slide, we know x, the distance was 0.8. We don't know dx dt, that's the rate of change or the speed of the other vehicle, plus 2 times y. Y is the distance the cruiser was from the corner, that was 0.6. dy dt would be the rate of change of the cruiser, which was negative 60, equals 2 times s was 1. That's what we found before using Pythagorean. And then ds dt was 20. That was how the distance between the cars was changing. So just simplifying this out, 1.6 dx dt plus negative 72 equals 40. Just doing your algebra, add 72 to both sides. 1.6 dx dt is going to equal 112. Divide both sides by 1.6. dx dt, or the speed of the car, is 70 miles per hour. So once again, related rates. Make a picture. Look at what you know. Write down the values that you've given, including rate of change. Write an equation. Typically, you'll be using something like a volume formula or a Pythagorean. Differentiate, and then at the end, substitute back in those values you know and solve for the missing component. Good luck!